Let's discuss a very important application of electric pressure, that is the calculation of force between hemispherical sections of a charged shell. Now let's have a look on a picture. Here this picture shows uniformly charged spherical shell with a surface charge density sigma coulomb per meter square, and the shell is of radius r. Here we wish to calculate the amount of force which the left half of the hemispherical shell will exert on the right half. Then in this situation, let's first consider a small elemental area ds on the surface of the shell. The direction of this area vector will exist outward away from the center in radial direction. And in this situation, if we talk about the charge on the elemental section ds, we can say it will be sigma ds, and this must be experiencing an electric pressure in outward direction. So we can say the force on elemental area ds due to electric pressure is, this can be written as df, which will also exist in radially outward direction. So this df will be electric pressure multiplied by the area ds. And in this situation, this will be the direction of force. So df factor will also exist in this direction. And say if this section ds is located at an angle theta from the base of this hemisphere, then we can also resolve this force into two perpendicular components. One will be df cos theta and other will be df sin theta. And here you can see, corresponding to this element, if we consider another element here, then the component of force perpendicular in perpendicular direction will be same as df cos theta, and df cos theta will cancel out and all df sin theta will be added up, corresponding to every force acting on each element. So in this situation, we can say net force on the right hemispherical shell is given as, this can be given as f will be integration of df sin theta, where we substitute the value electric pressure on a surface. We know it is given by sigma square by 2 epsilon naught multiplied by ds sin theta. And if we integrate it for the whole hemisphere, here sigma is a constant, so this can be written as sigma square by 2 epsilon naught multiplied by integration of ds sin theta. Now here, if this is the small segment area ds, if the area is divided into perpendicular components, if this angle is theta, here this will be theta, and this small section will be ds sin theta. So if we integrate this ds sin theta, the projection of this area on the base, which is ds sin theta, when we integrate, the total surface area of the hemispherical shell when projected on its base, the total area will be the area of its base, that is pi r square. So it can be directly given as sigma square by 2 epsilon naught multiplied by pi r square. That will be the force acting on the right hemisphere, and obviously it is due to the left part, and according to Newton's third law, right part will exert the same force on the left part. So this is the force which each hemisphere is experiencing, or it is the force between the two hemispherical sections of a uniformly charged spherical shell.